Now we're going to look at special types of simple graphs, and we're going to begin by looking at complete graphs on n vertices. These will be denoted by k sub n, and they're defined to be simple graphs so that between any pair of distinct vertices there is exactly one edge. So if we have two vertices, there's exactly one edge, and then as we add an additional vertex there, we simply join it to each of the other vertices by exactly one edge, and we continue. So as we've added this vertex, we need to connect it by an edge to each of the other vertices. Similar to these types of graphs, we will define both cycles and wheels. So the cycles will be defined to have at least 3 vertices, and we'll define the vertices to be connected by an edge if they are adjacent. So we'll organize the vertices in a cycle type pattern and add edges between any two adjacent vertices. So if we number the vertices, then we'll add edges to each adjacent set of vertices. We form wheels by simply adding a vertex in the center and connecting that to each of the outside vertices. So we take any cycle and add a vertex to the center and connect it by edges to each of the outside vertices. The n cubes are very relevant for you as they represent all bit strings of length n. So the graph q sub n is called an n cube. It has 2 to the power of n many vertices and represents all bit strings of length n, where there is an edge between two vertices that differ in exactly 1 bit position. So we see that we build up squares and cubes and so on, and we can represent this in terms of the bit string. So notice that there are edges connecting vertices corresponding to bit strings that differ in exactly 1 position. So notice that these 2 bit strings differ in the second position, these 2 also differ in the second position, these 2 differ in the second position as well, and these 2 differ in the first position. And notice these are not connected by an edge because they differ in both positions. Similarly for this one, and you can draw for yourself additional n cubes. Next we're going to look at bipartite graphs. So bipartite graphs are defined so that we can separate the set of vertices into 2 disjoint set of vertices, so 2 sets of vertices that are completely different, so that none of the vertices in each of those sets are connected by any edges, but then there are edges connecting from one set to the other. So what will make this more easy to understand is to think about coloring the vertices one of 2 colors, so either red or blue. So we look and notice that graph G depicted here is bipartite since we can color the vertices either red or blue so that any of the vertices colored red have no edges connecting any of them, and any of the vertices colored blue have no edges connecting them, but there are edges connecting some of the blue ones with some of the red ones, and vice versa. Notice that graph H is not bipartite since, for example, if we were to color this vertex A red, then since it is connected by an edge to both vertex F and vertex B, that would mean that both F and B would have to be colored a different color or be in a different vertex set, because no 2 vertices in the same set or with the same color can have an edge between them. So in this case, both F and B would need to be blue, but notice that there's an edge joining F to B, so that violates them being able to be in the same set. And since bipartite defines only 2 sets of vertices, this graph is not bipartite. We can also look at particular examples that we looked at before. So if we look at a cycle with 6 vertices, it looks like this, and it turns out that it is also bipartite. How do we see this? Well, simply we notice that we can simply put, or we can simply color every other vertex with the same color. So if we start here and this one is red, then this one can also be red and this one can also be red since they're not connected by any edges, and then the corresponding ones, this one, and this one, can be blue, and then we see that we have edges joining vertices on this side with vertices on this side, but no edges connecting these ones to these ones. So this is a representation of this same graph, but in a way that makes it look bipartite. On the other hand, not all cycles are bipartite graphs. Notice that C3, for example, is not bipartite, because, for example, if we were to color this vertex red, since it's connected to both of these vertices, they would both have to be colored blue, but again, as in our previous example, they're connected by an edge, so they cannot both be colored the same color in order to be bipartite, and so C3 is not bipartite. So next we're going to look at complete bipartite graphs, which are bipartite graphs with an additional characteristic.